Welcome. We want to discuss about computing the integrals, computing definite integrals. So at end of this lecture, we'll be able to do the following. One, calculate a definite integral using the definition of Riemann sum discussed in the last class. Interpret a definite integral in terms of area between the curve and x-axis. We'll relate antiderivatives to definite integral. We have already seen this in the last lecture about fundamental theorem of calculus. Calculate definite integrals of basic functions using antiderivative formulas. Again, as a consequence of fundamental theorem of calculus, differentiate functions that are given as definite integrals with variable upper and lower limits. So let's embark on this. So first things first, let's have some notation for integral computation. Recall this was discussed in the last class. So the idea is find to compute an antiderivative to compute a definite integral using fundamental theorem of calculus FTC. One needs to find either an antiderivative of the integrand. Yeah. And then once you find the antiderivative of integrand, you need to substitute. Then we need to substitute the upper and the lower bounds for the integration. Then evaluate this definite integral by subtracting the lower bound antiderivative value from the upper bound value of antiderivative. So, for example, suppose we want to integrate 1 to 2 of x squared dx. So, step 1 is to find the antiderivative. So, which is what we found out, antiderivative of x squared by using power rule is x to the power 3 divided by 3, right? So if we recall, antiderivative of x to the n is x to the n plus 1 divided by n plus 1 plus c if n is not minus 1, and it is ln of absolute value of x plus c if n is minus 1. So this is so-called power rule for antiderivatives. So here, so we find out antiderivative of x squared dx, which is x cubed by 3, and then we put a line like this to indicate upper limit is 2, lower limit is 1. Then we substitute, we evaluate by subtracting the lower bound antiderivative, which is 1 cubed by 3, from the upper bound antiderivative value, which is 2 cubed by 3. And the answer is 8 minus 1 divided by 3. So we have 7 by 3. So the vertical line with the subscript and the superscript, subscript is 1, superscript 2, is used. It's a small notation to indicate the operation of substitution, or to substitute and subtract, which is needed to finish the evaluation. So before we go further and do some problems, let's see some common mistakes which is made. First of all, one common mistake is dropping the dx notation at the end of integral. This is required because it tells you where the integrand ends and what variable you are integrating with respect to. So for example, integral a to b fx dx is not integral a to b fx. This has no meaning on the right hand. So the object on the right hand side has no meaning. This has no meaning whatsoever. So another one is checking the antiderivative. The antiderivative for integrand using differentiation, taking the derivative. before evaluation. So integral a to b fx dx is f of x a to b with f prime x equals to f of x. Yep. Now, then the other problem is, other common mistakes which is seen is dropping the lower and upper bounds of integration during the integration process. For example, 1 to 2x squared dx is not same as integration of x squared dx. These two are not equal, right? Yeah, and of course, which is not equal to this integration, because in this part here, you haven't written the limits of integration. So the limits of integration must be written when you're computing the definite integral. Yeah. So then second is forgetting to evaluate, forgetting to evaluate using the lower and upper limits of or upper bounds of integration that leads to the value of definite integral, and instead procuring a function. So note that the output of a definite integral is a function. Sorry, is a number, not a function. Okay. So note output of definite integral. Again, definite integral with constant limits is a number. Yeah. We'll discuss the case when it's a function, but another common mistake is switching the order of integration, switching the order of the lower bound and the upper bound of integration. For example, integral 1 to 2x squared dx is not same as, this is not same as what? This is not same as 2 to 1, as we have already seen clearly. But in this case, you have 1 to 2 is not same as 1 cubed by 3 minus 2 cubed by 3. It is 2 cubed by 3 minus 1 cubed by 3. So these are the common mistakes which we have to avoid. Oh, of course, we have to avoid all the mistakes, right? So, all right, so let's see some basic example of fundamental theorem of calculus, part 1. So suppose we have to have integral of 1 to 4 of integral from 1 to 4 of x cubed plus square root of x plus 1 by x plus x to the power 1, x to the plus 1 by x squared. So how do we go about it? So we'll use power rule here. So let's write down everything as proper power. So this is going to be 1 to 4 of x cubed. So first step, I'm going to write it as proper powers. This is going to be x to the power half plus x to the power minus 1 plus x to the power minus 2 dx. Now, if I apply the power rule for x cubed, it will be x to the power 4 over 4 plus x to the power half plus 1, which is x to the power 2, 3 by 2. So x to the power 3 by 2 divided by 3 by 2. So divided by 3 by 2 is same as multiplying by the reciprocal 2 by 3 plus x to the power minus 1. The power rule is different. It is going to be ln of absolute value of x. And for the other one, it's going to be x to the power minus 1 divided by minus 1. So divided by minus 1 can be written as minus x. And then we have to write limits of integration goes from 1 to 4. And then what do we get? We have 4 to the power 4. Substitute the upper limit plus 2 by 3. 4 to the power 3 by 2 plus ln of 4 minus 1 by 4. And then you substitute the lower limit 1 to the power 4 by 4 plus 2 by 3, 1 to the power 3 by 2 plus ln of 1 minus 1 by. And if we simplify this, we'll see that this is going to be 415 divided by 6 plus ln 4. Right. Let's move on to the next part now. So let's look at another example. Suppose we want to compute this integral 0 to 2x plus 1 dx using different ways. Okay. So one way to do that is using FTC1. It's a shortcut, computing the antiderivative. Using the definition of integral, which is basically limit sum definition, limit of sum definition, and then interpreting the problem in terms of area graphically. Now note that not all the problems can be done by all the three methods, but in this case, we have chosen a relatively simpler problem, which we can tackle using all the three methods. Yeah. So let's embark on that. So first of all, shortcut using FTC1 is the method of choice, and it is as it is the fastest. So we have 0 to 2 of x plus 1 dx. Again, I'll use the power rule. So x to the power 1, antiderivative is x to the power 1 plus 1, which is 2 divided by 2. Antiderivative of 1 is x. And then we have 0 to 2. That is going to be 2 square. Substitute the upper limit. So 2 square plus 2 plus 2. That is after substituting the upper limit. And then we have 0 square by 2 plus 0. And then when you simplify this, it's going to be 2 plus 2, which is 4. So this is how we compute this using FTC, fundamental theorem of calculus. Now let's evaluate this by using the Riemann sum. Okay. So we'll use Riemann sum as discussed in the last class. Riemann sum for n equally width rectangles using the right endpoint. So we can take delta x to be 2 minus 0 over n, right? That is going to be 2 over n. So we are dividing this interval into n parts. And the xi, which is the right endpoint, is going to be 0 plus I delta x, right? So the idea is you have this function from 0 to 2. You are basically drawing the heights. You're taking x1, x2, x3, dot, dot, dot. And suppose this is how your function looks like, so x plus 1. Then you're taking this and making a rectangle, right? So this was discussed in the last class, and here we are using that to, so the base is fixed, which is delta x, and the height is going to be f of xi. But what is my xi? Xi is 0 plus I delta x, which is going to be 2I over n. So this implies summation I going from 1 to n of xi delta xi. Recall, we were first finding this and then taking limit as n goes to infinity of this to find the value of the integral. So we have I going from 1 to n of 2I n divided by 2 by n. So if you think about it, this part gives the height, and the width of each of these rectangles is 2 over n. So now we can take the limit to find the integral. So 0 to 2x plus 1 dx is going to be n going to infinity, summation I going to from 1 to n, f of 2I by n divided by 2 time multiplied by 2 by n. This is going to be, but what is f of 2 by n? So this will be f of x is x plus 1. So f of 2 by 2I by n is going to be 2I by n plus 1 times 2 by n. Now we multiply this 2 inside, 2 by n inside, it will become 4I by n square plus 2 by n. Now we'll break the summation here. So we'll bring the summation to both of them and take common. So if I break this, from the first part, I can take 4 by n square common and write it as summation I going from 1 to n of I. From the second summation, I can take 2 by n common, and then it is just adding 1. So here we are. Now note summation I going from 1 to n of I is n into n plus 1 over 2. Whereas summation I going from 1 to n of 1, you're adding 1 n times, that is going to be simply n. So in this case, what we have is 4 by n squared. So we can now replace this value by, n into n plus 1 divided by 2. And here we will have n. So now this n can go below. So we have 4 times. Now one n will cancel and the other one will be 2 comes out. We have 1 plus 1 by n. And for the other one, we have 2. And now limit of n goes to infinity of this is going to be, what is limit of n goes to infinity of this? This part will become 0. So we have 4 by 2 times 1, which is 2. This is going to be 2 plus 2, which is 4. So we have done a problem now using the definition of Riemann sum. Now, third one, again, graphically. Now note that we may not be able to do graphically all the time, right? It depends on how simple the function is. So now we'll interpret this 0 to 2 of x plus 1 dx by interpreting in terms of area. Now this area, so if we draw the graph, this is how it looks like. It's a straight line. So when x is 0, y is 1. And when x is 2, y is 3. So you get a structure of the following form. Now we need to compute the area of this. So either you apply the formula for area of trapezoid, or you can break this into 2 parts from here. We break it, we get a rectangle with base what? With base as 2, area of 1, A1, which is base is 2, times height is 1, which is going to be 2. For the other part, the height is 2 and the base is 2. So area A2 is a triangle. So half base into height, which is 2 times 2, which is going to be 2. So therefore, area is the sum of area of a rectangle and a triangle. And hence 0 to 2 of x plus 1 dx is going to be a1 plus a2, which is 2 plus 2 is 4. Okay, so this is a presentation of finding the same integral using all the 3 methods. And I want to stress on it that it may not be possible all the time to use area, finding the integral using graphically or using the Riemann sum. Okay, so but FTC should work in almost all the cases we are going to work. Again, there are some functions for which there are no elementary antiderivative, but we will not work with those for most part of the course. All right, so now let's proceed further and discuss about some more interesting and definite integral and chain rule. So using chain rule, we can derive a formula for some more complicated problems. So we have d by dx of integral a to v of x of f of t dt. This is same as, if you recall, this would have been f of v of x according to our fundamental theorem, but you get an extra multiplication by d by dx of vx. This is a consequence of chain rule and fundamental theorem of calculus too. And this can be written as f of vx times v prime x. Okay, so this is the rule we are going to use further on. Now, so this is a scenario. So we'll work on few problems on this. But before that, let's ask the following question. What if the upper limit is constant and lower limit is a function of x? So for example, we have d by dx of ux to a of f of t dt. So how do we do this problem? So the one way out is to convert it into a previous problem. And how do you do that? We can interchange the limits of integration by putting the minus sign. This is one of the properties of definite integral we have seen in the last class. So this is going to be same as d by dx of minus of a to ux of f of t dt. And now we can apply the same thing. The negative sign comes out of the derivative. So we have minus of, now what is the derivative of this integral is going to be f of ux times multiplied by derivative of ux, which is u prime of x. Now, so now we have dealt with the case where the denominator, if the lower limit is a function and the upper limit is a constant. What if both upper limits and lower limits are what? Are functions. So suppose we are interested in d by dx of integral of ux to vx of f of t dt. How would we do that? So we can break this into the following form. So we can break it as ux to a f of t dt plus a to vx f of t dt. Now once we have that kind of breaking, now we can take derivative on both sides. So if you take d by dx of on both sides, you get what? So for this one, we have already seen the derivative is what? Is going to be minus f of ux times u prime of x. And for the first one will be f of vx times v prime of x. And hence we get this formula. Now let's work on a problem. Again, we have we have integral of t cube plus sine 1 plus t dt from 10x to x square. How do we do this? We will use FTC and chain rule formula. So here we have f of t is t cube plus sine 1 plus t. Ux, the lower one is 10x and the upper one is vx, which is x squared. So we have u prime x equals to derivative of this is 10 and v of x is 2x. Of x is 2x, right? So therefore, this becomes d by dx of 10x to x squared t cubed plus sine 1 plus t is going to be same as, so we use the formula from the previous one, which is f of, so this part is ux, this part is vx, and note the formula is f of vx times v prime of x minus f of ux times u prime of x. So what is f of vx? So f of vx times v prime of x minus f of ux times u prime of x. Now, what is f of vx? F of vx is wherever there is x, you're going to put v of x, which is you're going to put x squared. So it's going to be x squared the whole cube sine of 1 plus x squared. So instead of t, I'm substituting v of x, which is x squared, multiplied by v prime of x, which is 2x, minus f of ux. So now in f, I'm going to substitute 10x for x. So we get 10x the whole cube sine of 1 plus 10x multiplied by u prime of x, which is going to be 10. And this is our computation. Now note that you don't need to memorize any formulas. You could have done it directly, broken it here and applied it out. So this is how we use fundamental theorem of calculus to compute derivative of this integral. So the takeaway message is if both the limits are constant, then then the definite integral is a number. If the upper limit is a function, then it turns out to be a function as well. Thank you for your attention.